Okay, as we pick up here in chapter 14, uh, what we saw in chapter 13 was that we developed the conservation of mass and energy principles, applied them to reacting systems. And when we did that, we assumed that the reaction occurred as we stoichiometrically wrote the reaction to occur. And so we had fuels that combined with oxidizer to form products in certain proportions. And we made it very clear that we had to balance the atoms from one side of the equation to the other side of the equation. And so now we are going to look at a little different scenario in this particular chapter. And we are going to set up and define what we refer to as the equations of reaction equilibrium to determine the true composition of what the products consist of after going through the reaction. And so as a good example, let's look at a very simple reaction equation. This simple first reaction equation, 1418, is where we have 1 mole of hydrogen that reacts with 1/2 mole of oxygen to form 1 mole of water. And so that equation by itself is perfectly balanced. We have 2 atoms of hydrogen. We have 1 atom of oxygen, and they form water, which is 2 atoms of hydrogen and 1 atom of oxygen. And so back in chapter 13, we could write this. This would be the 100% theoretical combustion reaction. And our products would show up as 1 mole of H2O. We would look at the enthalpy of the reactants and the enthalpy of the products. We would take the difference and say that that was the heat released whenever that reaction occurred. But what we know also happens, especially when the products are at an elevated temperature and at certain pressures, we know that water doesn't just stay as water. Or better yet, what happens is hydrogen, the diatomic hydrogen, has a tendency to dissociate. And when it dissociates, it becomes 2 atoms of hydrogen. Likewise, oxygen at elevated temperatures can also dissociate and actually show up as 2 atoms of oxygen. And so we are not, with this particular reaction, we are not limited only to water as being the products. Anytime we have products that have hydrogen and oxygen associated with them, there is a chance that we could have hydrogen, diatomic oxygen, as well as monatomic hydrogen and oxygen also show up. The problem with that, though, is that when we are in chapter 13, when we balance this equation and we balanced atoms, we came up with the fact that the stoichiometric coefficient in front of the water had to be 1, and that there were no other components of the products. And so what we're saying now is maybe this hydrogen, this water might also be in the presence of some H2, some H, some O2, and some O. And so we could actually write this equation with 5 separate components. Now, the atom balance still has to hold, is that the total number of hydrogen atoms have to balance from the left side to the right side. Likewise, the total number of oxygen atoms have to balance from the left side to the right side. But now we have too many unknowns. And so we need to come up with some additional equations other than just the stoichiometric balance equation to tell us how much of those other components there are. And so we do this by taking a look at the changes that can occur in any particular reaction equation. And so when we say these three equations correspond to three separate reaction equations. And so at any given time, this particular equation could be happening. And the double arrow means that the reaction can actually be going in both directions. And so at any given time, we may see some hydrogen disappear that forms water. At any given time, we would also see some oxygen that disappears that forms water. And so for just this first equation, 1418, we can make the statement that the differential number of moles of hydrogen is going to be equal to the differential number of moles of water with a negative sign. So when if the number of moles of hydrogen increases, it's done at the expense of a water molecule disappearing. And so for this first equation, we can write this differential change in the number of moles. Likewise, if we could also say that for every mole of water that disappears or appears, let's say for every mole of water that disappears, a half a mole of oxygen is going to show up. And so we can write that with this particular form of the change in the number of moles between oxygen, O2, and water. And so we have these differential steps associated with each of those equations. We can also say for the second equation, we can say for every H2 that disappears, 2 H's will show up, or the opposite. And the same thing we can say for oxygen. And so what we're saying is that when we have a general reaction equation, as what we saw there, written in 3 different forms, we can write these equations generically. And that's what is being done right here at 1424. And so generically what we are saying is that molecule A and molecule B interact with each other to form molecule C and molecule D. And in order to balance atoms, we have a stoichiometric coefficient associated with each of the terms. And so this is a generic reaction equation that represents 2 molecules going to 2 molecules. Now, when I say molecules for A, B, C, and D, I could also be referring to atoms, okay? And so one doesn't always have to have 2 and 2. If one looked at this first equation, we actually have molecule A, which is hydrogen 2. We have molecule B, which is oxygen 2. But in this equation, we only have a molecule C, which is water. And so for 1418, we see that the stoichiometric coefficient nu sub A is actually equal to 1, and the stoichiometric coefficient nu sub B is equal to a half, and the stoichiometric coefficient C is equal to 1. And then there is no stoichiometric coefficient for D because that reaction does not have a D associated with it on the right-hand side. So any equation can be written with respect to these stoichiometric variables that balances the atoms. What this then tells us is that for each one of those, we can then write the differential change of the A, the B, the C, and the D in a form that looks like that. And so this is how we get that proportional changes associated with going from the left-hand side to the right-hand side of the equation. So what this then brings up for this reaction is that we can consider each of these terms to be equal to what is referred to as an extent of reaction, a small delta epsilon or d epsilon. And so what d epsilon is a differential change in the direction to the right. And so if I say that d epsilon is a positive, I'm saying that this reaction is going to the right, that C is being formed, D is being formed at the expense of A disappearing and at the expense of B disappearing. So a differential change to the right corresponds to this DNC and this DND being positive, and this DNA being a negative component, and the DNB being a negative component. And again, they are related by the stoichiometric variables. And so that parameter epsilon is referred to as the extent of the reaction. Again, if it's positive, the reaction is shifting to the right. If it's negative, the reaction is shifting to the left. If we came back to these three equations here, if we have a d epsilon that's positive, it says that this first reaction, hydrogen and oxygen are disappearing as water is appearing. If we have a positive epsilon for the second equation, it's telling us that monatomic oxygen is increasing at the expense of diatomic hydrogen. Hydrogen is disappearing. The third equation says that monatomic oxygen is appearing at the expense of diatomic oxygen decreasing. And so that would correspond to d epsilon as a positive. Now we could also have d epsilon being negative, means that the reaction is proceeding in that direction. So that is an important concept. As we take that d epsilon and we separate those four parts of the equation, we then can see that the differential change of the number of moles of each of the components can be written as related to that d epsilon. And again, the stoichiometric coefficients are involved there. And now what this allows us to do is, if you recall, we had a differential change in the mixture Gibbs energy that we defined. And we said that that differential change in the mixture Gibbs function at a given temperature and a pressure was simply related to the chemical potential of each of the components times the differential amount of that particular component, whether that component was decreasing or increasing. And so what we've done is we've taken the equation that we developed before at a given temperature and a pressure for a mixture, and we've then put it in terms of, if I went back, it was this equation right here, that we were talking about. So we come up here, it actually was related to this equation there. And we saw right here that it was related to what was happening in the mixture itself. And so now we can put in the left-hand sides here into each of these terms. Now there's a mistake here. There is no E associated with the reaction. And so in your textbook, this was an error, and so this term should not have been there. It should only have been A, B, C, and D. And so this term is not supposed to be there, and only the 4 terms. And upon putting in these into there, we then can bring out the d epsilon. And when we bring out the d epsilon, we then see that this differential change in the Gibbs function at a mixture temperature and pressure is then related to these 4 terms, d epsilon. And what we have said before at the beginning of this chapter was that at equilibrium, this mixture Gibbs function reaches a minimum whenever it reaches the equilibrium point. And so what's going to happen is these various, the extent of the reaction is going to be such that it's going to drive the mixture to a low value of mixture Gibbs function. And so that term is equal to 0. So the in parentheses here, that has to be equal to 0 because d epsilon is equal to 0. And so basically it tells us that this is what has to be equal to 0. And so we can then rearrange this, and when we rearrange it, what we have seen then is that at equilibrium for a given reaction equation, we have then the chemical potential of the 2 components on the left-hand side multiplied by their corresponding stoichiometric coefficient has to be equal to the chemical potential for the 2 components on the right-hand side times their stoichiometric coefficients for that particular reaction. And that then is the equation of reaction equilibrium. As you see at the bottom of this slide, it says in principle, the composition that would be present at equilibrium at a given temperature and pressure then can now be solved by solving that equation. The solution is then shown in the next section by employing what is referred to as the equilibrium constant. And so keep in mind that each of these chemical potentials correspond to an individual molecule or atom, and they are defined by the molecular atom's temperature and pressure within the mixture. And so if we are now interested in the equilibrium of a system that may have, as you see here, 1, 2, 3, 4, 5 different components. But since we only have 2 separate atoms, we can only, from chapter 13, write 1 equation. But now we have the capability, because we've added these 3 equations, we now have a separate equation for each one of those based on the particular components at a given temperature and pressure. And so that gives us then 5 equations and 5 unknowns. Instead of having just the 2 atom equations, we now have 3 additional reaction equations, which would then give us the effect of having 5 equations and 5 unknowns. As we go a little bit further, if taking this equation here that's written in terms of the chemical potential, recall before that I said that the chemical potential for each component, if the component itself can be treated as an ideal gas, is simply related to has two parts associated with it. The first part being the Gibbs function at a reference pressure, and the second part which corresponds to the partial pressure of that particular component in the mixture, and with the RT in it. So this is the chemical potential for component A at a given temperature and pressure for the mixture. This is the chemical potential associated with component B. This is the chemical potential associated with component C, and this is the chemical potential associated with component D. And so again, this equation right here is this equation, which is the equation of reaction equilibrium. And so we can go further, take this big equation here, and we can separate some things and send it over to the left side of the equation, and we can separate other things and send it over to the right side of the equation. When we do that, we take the first two terms here, these two terms, this two terms, and this two terms, and we can throw them to one side of the equation, and we then get this right here. And in essence, what's happening is here is the first term, here is the second term, minus this term, minus this term. And then everything that would show up on the other side of the equation has the RT, as well as the value, the stoichiometric coefficient. And so we see the RT, and then we have each of these four terms here, right here. So we see in this particular equation that we can write the equation associated with the ideal gas mixture of a component that has A, B, C, and D, and by separating the terms and throwing them to the left-hand side, these four terms here becomes the capital G0 delta term, and then we have minus RT times these terms here that involve the partial pressures. If we take this equation then, it can be shown that the delta G then also can be related to the enthalpy as well as the entropy. But most importantly, if we were to go back here and we were to say that this was delta G0 and divide it by minus RT, what we have left over on the right-hand side of the equation then are these natural logs of the various partial pressures, and they are multiplied by the various mole fractions of the individual components within the mixture, as well as the nus, which are the equilibrium or the stoichiometric coefficients for that reaction equation. And so it turns out then that we get this equation, and basically this equation tells us then that the delta G0 over the magnitude of R times the temperature of the mixture is then directly related to the partial pressures of each of the components raised to the powers associated with that particular reaction equation. It turns out that this term here is only a function of temperature, because we can find at a given temperature, we can find the value of G0 And if this is only a function of temperature, then the natural log of this combination here would also be only a function of temperature. And what has happened is the portion that's within the natural log is stated as being equal to the equilibrium constant, capital K. And so capital K is tabulated as a function of temperature. And so for a particular reaction, we then can, for a given temperature, we can then determine its equilibrium constant, and then we can use that to then equal this, which is related to the mole fractions as well as the mixture pressure. And so the key to this reaction equation is that we obtain for a particular reaction as a function of temperature this left-hand side that we introduce as a equilibrium constant at a given temperature. We then can use that to determine the mole fractions of the individual components at a given pressure. So as an example, in our textbook, we have a table, and the table lists for various reactions. And here you can see some of the reactions that are considered. Here's one that is water that is reacting to form H2 and 1/2 O2. It actually is the reverse of the reaction that we saw before. But when we look at that particular reaction at a given temperature, let's say 3000 Kelvin, we can come over and we determine that the equilibrium constant is a number that's associated with this 1.343, negative 1.343. Now, the table has been presented in terms of the log base 10 of K. And so at 3000 Kelvin, this number really is 10 raised to the minus 1.3 power. Okay, if I were to go up to this 2600, and if I would look at the equilibrium constant, this equilibrium constant, or the log base 10 of this equilibrium constant, implies that the constant itself is approximately 1 over 10 to the 2 power, or the equilibrium constant is about 0.01, 1/100th. And so one has to be careful how you read this table, because the table is the equilibrium constant taking to the log base 10. And so what that then tells us is that at 2600 Kelvin, for this particular reaction, we see that the combination of mole fractions and the stoichiometric coefficients basically tell us the direction at which the reaction would be going. If we come back to the definition of this K, for that temperature, we saw that the K was equal to about 1/100th, or 0.01. And so if we look at the definition, if we were to assume that the pressure was equal to the reference pressure, then this term would just go away. And what we then have is we see that the mole fractions of the left-hand side or the right-hand side of the equation are going to be related to the mole fractions of the left-hand side of the equation in this fashion. So at that particular temperature, we saw that this ratio was 1 over approximately 100, which said that the A and B's overweigh the C's and the D's. And so up here, what that tells us is that at 2600, this number right here tells us that this reaction is going to primarily stay in toward the left-hand side, which is the H2O versus the H2 and the O2. Okay, again, because we keep in mind what our equation was. Our equation was this, and so for the equation that's written in this particular fashion, again, my mistake is that this equation has been written such that the A and the B corresponds to this, and this is the C and the D. And so since we see that the equation itself is written like this, it's basically saying that the A and the B, the numbers associated with the A and the B, are greater than the numbers associated with the C and the D. And so this table would tell us, since this is the A and the B, and this is the C and the D, this would tell us then that the reaction is favoring the direction associated with that, the value of that equilibrium constant.